Compartmental models in epidemiology, Wikipedia audio. Compartmental models are a technique used to simplify the mathematical modeling of infectious disease. The population is divided into compartments, with the assumption that every individual in the same compartment has the same characteristics. Its origin is in the early 20th century, with an important early work being that of Kermack and McKendrick in 1927. The models are usually investigated through ordinary differential equations, but can also be viewed in a stochastic framework, which is more realistic but also more complicated to analyze. Compartmental models may be used to predict properties of how a disease spreads, for example the prevalence or the duration of an epidemic. Also, one can understand how different situations may affect the outcome of the epidemic, e.g., what the best technique is for issuing a limited number of vaccines in a given population. The SIR model. The SIR model is one of the simplest compartmental models, and many models are derivations of this basic form. The model consists of three compartments: S for the number S susceptible, I for the number of I infectious, and R for the number RE covered. This model is reasonably predictive for infectious diseases which are transmitted from human to human, and where recovery confers lasting resistance, such as measles, mumps, and rubella. These variables represent the number of people in each compartment at a particular time. To represent that the number of susceptible, infected and recovered individuals may vary over time, we make the precise numbers a function of T, S, I and R. For a specific disease in a specific population, these functions may be worked out in order to predict possible outbreaks and bring them under control. As implied by the variable function of T, the model is dynamic in that the numbers in each compartment may fluctuate over time. The importance of this dynamic aspect is most obvious in an endemic disease with a short infectious period, such as measles in the UK prior to the introduction of a vaccine in 1968. Such diseases tend to occur in cycles of outbreaks due to the variation in number of susceptibles over time. During an epidemic, the number of susceptible individuals falls rapidly as more of them are infected and thus enter the infectious and recovered compartments. The disease cannot break out again until the number of susceptibles has built back up as a result of offspring being born into the susceptible compartment. Each member of the population typically progresses from susceptible to infectious to recovered. This can be shown as a flow diagram in which the boxes represent the different compartments and the arrows the transition between compartments, i.e. For the full specification of the model, the arrows should be labeled with the transition rates between compartments. Between S and I, the transition rate is beta I, where beta is the contact rate, which takes into account the probability of getting the disease in a contact between a susceptible and an infectious subject. Between I and R, the transition rate is gamma. If the duration of the infection is denoted D, then gamma equals 1/D, since an individual experiences one recovery in D units of time. It is assumed that the permanence of each single subject in the epidemic states is a random variable with exponential distribution. More complex and realistic distributions can be equally used with few modifications. The dynamics of an epidemic, for example the flu, are often much faster than the dynamics of birth and death, therefore, birth and death are often omitted in simple compartmental models. The SIR system without so-called vital dynamics described above can be expressed by the following set of ordinary differential equations. This model was for the first time proposed by Okermack and Anderson Gray McKendrick as a special case of what we now call Kermack-McKendrick theory, and followed work McKendrick had done with Ronald Ross. The SIR model is dynamic in three senses. This system is nonlinear, and does not admit a generic analytic solution. Nevertheless, significant results can be derived analytically. Firstly, note that from it follows that, expressing in mathematical terms the constancy of population, n. Note that the above relationship implies that one need only study the equation for two of the three variables. Secondly, we note that the dynamics of the infectious class depends on the following ratio. The so-called basic reproduction number. This ratio is derived as the expected number of new infections from a single infection in a population where all subjects are susceptible. This idea can probably be more readily seen if we say that the typical time between contacts is T(c) equals beta 1 equals \beta, and the typical time until recovery is T(r) equals gamma 1 equals \gamma. From here it follows that, on average, the number of contacts by an infected individual with others before the infected has recovered is T(r)/T(c)/T. By dividing the first differential equation by the third, separating the variables and integrating, we get transition rates. Biomathematical deterministic treatment of the SIR model. And r, 0, are the initial numbers of, respectively, susceptible and removed subjects. Thus, in the limit, t, plus, the proportion of recovered individuals obeys the following transcendental equation. The SIR model without vital dynamics. The force of infection. Exact analytical solutions to the SIR model. The SIR model with vital dynamics and constant population. The SIS model. This equation shows that at the end of an epidemic, unless S, 0, equals 0, not all individuals of the population have recovered, so some must remain susceptible. This means that the end of an epidemic is caused by the decline in the number of infected individuals rather than an absolute lack of susceptible subjects. The role of the basic reproduction number is extremely important. In fact, upon rewriting the equation for infectious individuals as follows, it yields that if, then, elaborations on the basic SIR model, i.e., there will be a proper epidemic outbreak with an increase of the number of the infectious. On the contrary, if, then, i.e., independently from the initial size of the susceptible population, the disease can never cause a proper epidemic outbreak. As a consequence, it is clear that the basic reproduction number is extremely important. Note that in the above model the function models the transition rate from the compartment of susceptible individuals to the compartment of infectious individuals, so that it is called the force of infection. However, for large classes of communicable diseases it is more realistic to consider a force of infection that does not depend on the absolute number of infectious subjects, but on their fraction derived an exact analytical solution to the SIR model. In the without vital dynamics setup, for S, U, equals S, T, equals S, etc., it corresponds to the following time parametrization. The MSIR model. For T equals U 1 N beta S N R 0 plus rho ln S S 0 S D S ds rho equals gamma n beta with initial conditions S 1 I 1 R 1 equals S 0 N R 0 S 0 R 0 comma equals NRSR U T 0. Fortunately, it is possible to find an analytical solution to this model, such that the basic reproduction rate is greater than unity. The solution is given as where I equals chi n slash beta equals backslash chi n slash backslash beta is the endemic infected population, chi equals beta gamma and v equals I slash I 0 1 slash I minus 1. As the system is assumed to be closed, the susceptible population is then S T equals N I T. For many infections, including measles, babies are not born into the susceptible compartment but are immune to the disease for the first few months of life due to protection from maternal antibodies. This is called passive immunity. This added detail can be shown by including an M class at the beginning of the model. To indicate this mathematically, an additional compartment is added, M, which results in the following differential equations. Some people who have had an infectious disease such as tuberculosis never completely recover and continue to carry the infection, whilst not suffering the disease themselves. They may then move back into the infectious compartment and suffer symptoms, or they may continue to infect others in their carrier state, while not suffering symptoms. The most famous example of this is probably Mary Mallon, who infected 22 people with typhoid fever. The carrier compartment is labeled C. For many important infections there is a significant incubation period during which the individual has been infected but is not yet infectious themselves. During this period the individual is in compartment E. Assuming that the incubation period is a random variable with exponential distribution with parameter A assumption that birth and death rates are equal, in general, n is a variable. For this model, the basic reproduction number is R 0 equals A mu plus A beta mu plus gamma dot equals dot. Similarly to the SIR model, also in this case we have a disease-free equilibrium and an endemic equilibrium EE, and one can show that independently form biologically meaningful initial conditions. It holds that in case of periodically varying contact rate, beta T, the condition for the global attractiveness of DFE is that the following linear system with periodic coefficients is stable. The CEASE model takes into consideration the exposed or latent period of the disease, giving an additional compartment, E. In this model an infection does not leave any immunity, thus individuals that have recovered return to being susceptible again, moving back into the S compartment. The following differential equations describe this model. For the case of a disease, with the factors of passive immunity, and a latency period, there is the Messier model. An Messier's model is similar to the Messier, but the immunity in the R class would be temporary, so that individuals would regain their susceptibility when the temporary immunity ended. It is well known that the probability of getting a disease is not constant in the time. Some diseases are seasonal, such as the common cold viruses, which are more prevalent during winter. With childhood diseases, such as measles, mumps, and rubella, there is a strong correlation with the school calendar, so that during the school holidays the probability of getting such a disease dramatically decreases. As a consequence, for many classes of diseases one should consider a force of infection with periodically varying contact rate, with period t equal to 1 year. Thus, our model becomes epidemic outbreaks of some infectious diseases as interplay between the period of the contact rate oscillations and the pseudo-period of the damped oscillations near the endemic equilibrium. Remarkably, in some cases the behavior may also be quasi-periodic or even chaotic. In the case of some diseases such as AIDS and hepatitis B, it is possible for the offspring of infected parents to be born infected. This transmission of the disease down from the mother is called vertical transmission. The influx of additional members into the infected category can be considered within the model by including a fraction of the newborn members in the infected compartment. Diseases transmitted from human to human indirectly, i.e. malaria spread by way of mosquitoes, are transmitted through a vector. In these cases, the infection transfers from human to insect, and an epidemic model must include both species, generally requiring many more compartments than a model for direct transmission. For more information on this type of model, see the reference Population Dynamics of Infectious Diseases, Theory and Applications, by R. M. Anderson. Other occurrences which may need to be considered when modeling an epidemic include things such as the following. It is important to stress that the deterministic models presented here are valid only in case of sufficiently large populations, and as such should be used cautiously. To be more precise, these models are only valid in the thermodynamic limit, where the population is effectively infinite. In stochastic models, the long-time endemic equilibrium derived above does not hold, as there is a finite probability that the number of infected individuals drops below 1 in a system. In a true system then, the pathogen may not propagate, as no host will be infected. But, in deterministic mean field models, the number of infecteds can take on real, namely, non-integer values of infected hosts, and the pathogen may still persist in the system with a finite number of infected hosts, less than 1 but greater than 0. The Messiers model. Variable contact rates and pluriannual or chaotic epidemics. Other considerations within compartmental epidemic models. Vertical transmission. Vector transmission. Others. Deterministic versus stochastic epidemic models.